that you thought you would kind of like to have a little more of a video overview of the chapters in addition to just reading through them. So I thought, let's try it in chapter 4, see what you think. And if you kind of like this, we can do it for all the chapters. But let's talk a little bit about sequential containers. And specifically in this section, we're going to try to understand this STL library. And even though you've used vectors before, we'd like you to really understand what's going on in them and um, really to understand other sequential containers as well as linked lists and other uh, data structures that you'll be using for this next lab. We also like to help you kind of understand an iterator and how to use an iterator to go through data structures that are not sequential, like a list. So you've probably used vectors a lot and have thought about them as being arrays. We're going to have you kind of use raw arrays, which allow you to get right down to the hardware in your machine for the data structures that you're going to be writing. The standard template library provides you with a number of different flexible classes that can be used for storing data items. And really when it comes right down to it, that's the most important thing in terms of writing a program, is to figure out what the data structures are and how to store them in a container and access them. So we're going to you've probably used a index with the square brackets to get into an array, but some things, for example, a list structure, doesn't have the ability to index into that structure. We'll also talk about trees later in the semester, and you can't really index into a particular element of a tree. So we need some way of getting through any kind of a data structure just by knowing the beginning and end of that data structure. So the way we do this is we'd really like to use iterators, and they allow us to go through a data structure, whether it's a vector or a list, and access all of the elements in that data structure. So let's get started and talk a little bit about template classes and specifically the vector class. And so you've used it before, and you notice that there's this notion of a being able to say I've got a template class, like this could be a vector of some particular type. And we will actually be writing this kind of thing before, and the way we implement it is through this template keyword. And so it's a kind of a class that can store any kind of a collection of information. And you've noticed before that you can have vectors of strings or vectors of ints or vectors of anything, and that's really what we're trying to build with this class. Okay? And so in this particular case, we're going to start by declaring a template for a container type here. And now any place that we use this T, it will replace the T with whatever type we're using. So if we declared some container pointy brackets int, then that T would be the int part. Okay? And so that's kind of, you'll get the idea as we do this. So if we put int in there, then any place inside of our container definition that used T, we would substitute an int. But we could also use it for a custom object like a person thing. Okay, so kind of an indication of templates, and we'll talk a lot more of them throughout the semester. So vector is a template class. It's a lot better than arrays because we can increase or decrease its length, and we can insert elements at a specific position in the middle. You can't really do that without shifting all the other elements around. And we can also remove an element from a particular place. And by the way, vectors are there's a lot of work that's gone to make them fast, and you can actually compare the performance of a vector to array, and most of the time it's just as fast. So if we wanted to create a telephone directory, then we would, we could potentially add entries to the end, and if you wanted to find something in there, we could search through it. If an insertion for a vector is not at the end of the vector, then we can go ahead and shift everything after the element we want to insert, and then possibly copy everything from that point down into a new spot, and then we'd have room for our new element in the vector. Vector has this thing called size that we can use to figure out how many elements are currently in the vector, but we can, as soon as we have added so many things that its size is equal to capacity, then it will automatically allocate more space, copy everything over to the bigger space, and you don't even have to mess with that. So that's one of the real benefits of using a vector. Again, we talked about how we can declare it. Again, vector, we're just going to put inside of the pointy brackets the type that we want, and that will then declare a vector of that particular type, and you've done that a lot in 142 as well. Again, if we declared this vector of strings, it will start out empty, and then we can do push back to push things onto our vector. Okay. We can also use the square brackets to index into our vector, into things that we have pushed on there. We can also insert something. For example, we can insert a position 2, and you'll notice that it takes Jumpy and Happy and pushes them into the next locations and puts 2 at that particular position for vector. We can also use push back, which takes our existing list and just adds a new element to the very end of the vector. And this is all kind of familiar to you, but just going through them a little bit, you may not have used some of these. You may not have used erase, which allows me to pick a particular element and delete it out of the middle of a vector. And you'll be doing some of these when you are looking at the next lab where we look at expressions. Again, we can use this subscript that allows me to index to a particular element here and access something that's not at the beginning of the container. You can also replace an element by using that square bracket thing, and that will go ahead and replace what's at position 2 with a new element. A lot of this is pretty familiar to you. I'm not sure this is really all that important, but here's the specifications of the vector class. This is found in your textbook. It tells you what all the functions are that you can actually call. You can push on the back, you can pop from the back, and one thing about a vector is you can really either put things onto the front or the back, and it's very flexible. Okay, let's go ahead and move on. One of the things that's not familiar to some students is when you say that you want to use these square brackets to index into your vector and get a particular element, you're actually calling a function called @ and passing it as a parameter the element that you actually want to get. And when we start writing our containers, we're going to do the same thing, and we'll show you how you can actually use this operator overloading to actually call a particular function on that vector. And so both of these are equivalent in what they do. And so you could also put them on the left side of the equals, and we could say v at 3 is equal to some other value, and it will change the vector at that particular position. We're not going to talk a whole lot about vectors the text goes into them quite a bit, and you've had a lot of experience with using them. Normally, you're going to have you may have said integer before, but it's actually more proper to use size underscore t as a type for something you're going to index into your array with, and that will allow you to compare to the size element of a vector. They're going to talk in the text about a phone directory application. And so now the most important thing is, how do we actually implement a vector class? And the reason we're going to go into this is we're going to talk about underlying the specification of a vector class, or which we just showed you how you can use it, is how it's actually implemented. So let's kind of take a look at this. They're going to go ahead and create a vector class, and it's going to have functions. So notice here that we're saying it's a template class, which is going to have a type name item type, and then that any place you see that item type, for example here we're going to have a pointer to an item type, it will replace that with whatever type you've defined for this particular container. So if we said we want to have a vector of ints, then this would be an int pointer, the data down here. Okay? And so they're going to go ahead and show you how you'd actually implement a vector. It's going to be inside of this namespace KW, so you can differentiate it from the namespace STD that you're often using. Okay? And so we're going to keep track of our current capacity, and then we're also going to keep track of the size, which will start out with allowing 10 elements. Then as we add more things, when we get to 10, it's going to say, okay, I'm going to now increase my capacity to 20, allocate more space, copy everything over into the new place, and then my capacity will increase. Okay, so we're going to, again, we've got to use something that's available in our hardware, and a C++ array is probably the closest thing that we have to hardware. And the way this will look is, here's a bunch of elements that we currently have. We have this filled up to num items. Here's our current capacity, and we can keep adding items until we get to our current capacity. Now, one thing to think about, you don't need to really worry about this now, but you'll notice that all you do is you just say include vector, and since it's a template class, all of the implementation is inside of the include file. So you don't actually have to compile with an implementation of a C++ file. And when you get to writing your own template classes, you're going to want to put them all inside of the include file, even though now we're telling you not to do that, but to break your code up in different C++ files. So we're going to have a constructor at this point, which will allow us to initialize our, in this particular case, that data type pointer that we had, and do other things. We're going to actually put in a swap function that allows me to swap elements and values inside of my container. And we would also like to allow you to use the subscripting operator or the square brackets. And so we mentioned that we're going to call that using we're going to call a @ function with that operator. So here we go. Here we're defining what the operator is. When you call square brackets, you're actually just calling a function and passing it this index, which is going to be the value that's inside of the square brackets. Okay. We're not going to talk a lot about these details, but you need to be careful and use the const version when you're applying the subscript operator or it won't work. Okay, so now if we take a look at this, here is my operator, square brackets. I'm now going to go in here, I'm being passed this parameter index. I'm now going to say if my index is between 0 and the end of my filled part of the, if it's not inside of the correct range, I will go ahead and throw a exception. And we'll talk more about exceptions when you start writing your own things. Otherwise, we're just going to go into my array of the data and return the value that was passed to us for index. So often this square bracket thing feels like it's magic, but it's actually just a function that is passed the index that's inside of the square brackets. Okay. Let's see. I think this is all that important. Let's look at some of the other functions. Push back then appends an item to the end of the vector. So what it's actually going to do is, we've already kept track of what new items is. We're going to go ahead and put the new value where new items pointed to, and then we're going to move new items to the next space in the array. Again, if we have gotten to the end, we've already hit our current capacity, then we're going to allocate new space and copy everything over to that new space, and then go ahead and put our new value into the space that we've expanded. If we want to insert into the middle of an array, then we're going to, if we want to insert at index, we're going to take whatever was there, move it to the next spot, take whatever was in that spot, move it to the next spot, all the way to the end of the stuff that we've allocated. So if you think about it, inserting in the middle of a vector is probably one of the most time-consuming operations that you can perform, because we're going to have to move everything down to make space for it. And you can actually see this if you run benchmarks on your code. So again, if we want to insert something, we'll figure out if we're in the middle or not. We'll see if there's enough space before current capacity. If not, then we're going to go ahead and double the current array that we have, and then we're going to move everything from where I am to the end of the allocated space down one, so that we can insert our element into the vector. So I'm hoping that as you see this, even though you've used vectors before, that this will give you some insight into actually what's going on. If we want to erase something out of the middle, we're going to do just the opposite. We want to erase something at this index. We're going to take the next one, move it in here, the one after that, move it into the next spot, and so forth until we're through with the number of items, and then we'll decrement that num items. Okay. Again, here's code for what we're going to do here. I hope you're kind of noticing that even though the vector seems like a pretty magic data structure, that there's not all that much code to actually make this work. This reserve function we kind of talked about, we're going to double the size of the array every time we run out of space, just in case we need it. And then we're going to use this function called new, which allocates some new space for us in the heap, and then we're going to copy everything from 0 to the end into that new space. Then we're going to delete the space we had before and point to the new data. So you're going to become real familiar with new and delete as we work through this class. And this kind of memory management is really a very important skill for you to have from your data structures class. So if we take a look at this, another part of this particular section of the class is we're going to talk about big O notation. And what big O notation is kind of an estimate of how long it is going to take to do any particular operation. So if we move something, insert or remove something from the middle of a vector, then we're going to have to shift. Let's say that there are n items inside of our array. If I remove the very first one, I'm going to have to shift all n of them, n minus 1 of them, over one to the left. Similarly, if I want to insert something, I'm going to say I want to insert something right at the beginning, I'm going to have to shift everything to the right. So it's still an order n operation. So if we can talk about this, and this order notation, what it basically says, I don't know exactly how many instructions it takes to shift an item to the right or the left, but there's about n of those operations that I have to take. So this is kind of a way of comparing operations, and we're going to find out in a few minutes here that when we use a list, it actually has order 1 complexity to insert something or delete something from the middle or the beginning of a list. And so that's kind of a way of comparing different data structures. There's also a copy constructor, an assignment operator, and a destructor that are associated with a vector. Again, copy constructor is invoked when you pass an object to a function, when it's returned from a function, or when you set one object equal to another object of the same class. So you can imagine saying vector 1 is equal to vector 2, and it's going to want to copy everything in the vector, not just change one particular value. Okay? So in this particular case, all we're going to do is when we and let's introduce the notion of a shallow copy versus a deep copy. Again, if we say a shallow copy, we can just point both items at the same data. However, if we want to do a deep copy, then we're going to have to copy everything over to a new data space. And a lot of times we'll end up doing a shallow copy until we've modified. If both of them access the same data but don't write to it, then we can just do a shallow copy and point them both to the same data. As soon as we change something, then we want to go ahead and do a deep copy so that we can have two different values at a particular point in our array. I don't think this is terribly important. You'll probably want to take another look at this once you have written your own containers. However, here's a case of a deep copy. We're going to actually go through every element, which is an order n type operation, and we get that occurring whenever we pass a vector into a function and when a vector is returned from a function. So as you're writing code, you kind of need to be aware of when you actually do a deep copy so that you can make good coding decisions. So again, we mentioned that if we have two vectors and assign them to each other, we're actually going to have to do this kind of a copy operator. Okay. So if we do normal assignment, it makes a shallow copy. We can override it if we want to have truly independent copies. And let's talk about the destructor. Again, the destructor on a vector, we mentioned that initially a vector is going to allocate a default amount of space, and then we're going to call new to allocate more space. So we have to make sure that we delete all of the memory that we've allocated in the destructor. Okay. And we also need, we could possibly have a vector of vectors, and so we would need to call a destructor on whatever type was inside of the vector. Here's again the notation for a destructor, and we're going to go ahead and call delete with the square bracket notation so that it deletes whatever that was, even if it was an array. Okay, so that's kind of an overview of vectors and how they're implemented, and hopefully that's helpful to you. And if you like these videos, we'll make some more of them.